Carnot engine. Carnot engine, we talked before about the heat engine. Heat engine where we have a clockwise cycle. Omega of the cycle, of the entire cycle is positive. We have Q hot and you have Q cold. Here we have the Carnot engine. It's an ideal, it's not real. It's an ideal cycle. Okay. Also, it's a reversible cycle. When I say reversible, so we start by the point A to B to C to D, and we come back to the point A, and we can have again the same initial state. Okay, it's a reversible cycle. This cycle is called Carnot. This engine is called Carnot cycle. It's between two reservoirs. We have T hot and T cold, like in the case of the vehicle engine. We have T hot and T cold. And this kind of engine has the most efficient possible. Okay, the efficiency of E Carnot of this cycle is the upper limit of all other engines. Let me explain the Carnot cycle. You know, in general, it's a closed cycle. We start by the point A. It's a heat engine. When we have a heat engine, so we have two reservoirs. We have T hot and T cold. Okay, T hot and T cold. Why? First of all, this cycle is an ideal cycle. You cannot have it in the nature spontaneously. You must have an external control. An external agent can control this kind of cycle. Okay, first of all, we go from the state A to the state B by an isothermal expansion. So the volume increases. The cylinder is in contact with the energy reservoir at T hot. Why? Because when we increase the volume, so in general, P decreases and T decreases. Okay, when we increase the volume, the pressure decreases and also the temperature. Okay, because PV equals to an RT. If we increase the volume, the temperature decreases. In order to keep the temperature constant, we must give some quantity of heat. So we put here the cylinder in contact with with an object with a temperature high, with T hot, to give Q hot to the system. When the temperature decreases, I give Q hot to increase the temperature and to have the same temperature constant, T constant. So the volume increases, P decreases, T decreases. To keep T constant, we add Q hat. Okay, we have Q hat. So from A to B, we have we increase the volume, so the work AB must be positive, and we have Q hat, which is positive. The second point. So first of all, we go from the point A to the point B with isothermal process. Here we have VA and here we have VB, P, V, and T is constant. TA equals to TB. TA equals to TB equals to TH. TH is the temperature of this reservoir. Okay? We go to the second point. From the point B to the point C. Here we increase the volume, but with an adiabatic process. So when I say adiabatic, so we don't have any exchange of energy. We don't have heat. For this reason, we have a thermal insulation. We have an isolated system. Isolated system. Q equals to 0. And the volume increases, so omega between B and C must be positive, and QBC equals to 0. You know, in general, if we increase the volume, the temperature and the pressure decreases. So here we are at the point B, and from B to C, it's like this, where Q equals to 0. Okay, here we have VC, and here we have VB, and here we have VA. Okay, we go to the third point. At this point, the gas is in contact with a cold reservoir where T equals to T cold, TC. If you go back to the vehicle engine, we are in the last step where the gas will go out, where the gas is in contact with the external environment medium. Here at this point, we decrease the volume decreases. In general, when we decrease the volume, P increases and T increases. But between C and D, we have an isothermal process. I want to have an isothermal process. To keep T constant, we have to get out some quantity of heat. Okay? We have to reduce the temperature. So we have the cylinder in contact with T cold. So we can say to keep T constant, we have Q cold, lost by the system. How? By the thermal contact between the cylinder and the reservoir with T cold. In this case, we have omega, the volume decreases, so omega must be negative between C and D. So first of all, we have isothermal. The second point, we have adiabatic. And the third one, we have isothermal. We go to the last one. So here we go from C to D, like this, with T constant. TC equals to TD equals to T cold. Okay, T cold. Now, the last point, from D to A, like this, it's an adiabatic process where the volume decreases. In this case, omega dA must be negative, and Q dA equals to 0 because adiabatic. So what you have to know now, the Carnot cycle consists of isothermal expansion, AB, where we have Q hat, QAB is positive, adiabatic expansion, BC, with BC we have Q equal to 0 and omega is positive, isothermal compression CD, where the volume decreases, we have a positive value of omega, and we have Q cold, and finally we have adiabatic compression between D and A, where we have omega is positive and Q equal to 0. Okay, so you have to know these steps for each one. Let me write quickly. Isothermal between AB. Here we have AB. We can say omega AB must be positive, and you know QAB is positive. Adiabatic here, omega BC is positive, and QBC equals to 0. Isothermal CD is negative, and QCD is negative. And finally, we have omega dA is negative because we decrease the volume, and we have Q dA equals to 0. First of all, TA in the first one, here we can say TA equals to TB equals to T hat, and in this one, TA TC equals to TD equals to T cold. Okay, and you know, for any, the total work of the cycle equal to the area enclosed by the curve here. This is the total work inside. And delta E of any closed cycle equals to O. So omega of the cycle equals to Q hat minus Q cold, or Q hat equals to omega plus Q cold. What is the efficiency of a Carnot engine? You know, in general, the efficiency equals to omega of the cycle divided by Q hat. Omega, finally, we have 1 minus Q cold divided by Q hat. For Carnot cycle, Q cold divided by Q hat equals to T cold divided by T hat, or equals to T high divided by T low. Okay, in the next videos, we have to calculate this relation. How can we calculate Q cold divided by Q hat equals to Q T hat divided by T low? So if you substitute this value, you get finally E Carnot equals to 1 minus T cold divided by T hat. I repeat, you can put it 1 minus T of the high reservoir, T high, divided by T cold of the cold reservoir. Okay. E Carnot must be less than 100. You can say E Carnot less than 1 as a value. In percentage, we have 100. Theoretically, a Carnot cycle heat engine can run reverse. It means we come back to the initial state. It's a reversible process cycle. You will see in the next video when I say Carnot machine, Carnot cycle, it means the entropy equal to 0. The change of the entropy equal to 0. So we start from the point 1 and you go back to the same point. So we don't have, we go back exactly to the same state. So we don't have a disorder. Delta S equal to 0. And T is in